Now, in the last paper before the coffee break, which is a hint not to overrun the time, we have a contribution from the home team, and Dr. Raybec is giving what is, I think, his first contribution to an international public audience. So let us wish him well. The paper is entitled Generation of Adsorbed Alkyl Species by Thermal and Photodissociation Processes.
Mr. Chairman, ladies and gentlemen, my lecture dealing with the generation of alkyl species on palladium surface. Alkyl groups are important in many of reactions. We produce alkyl species by the dissociation of alkyl halides. The other importance of alkyl halides is the catalytic destruction of halogenated hydrocarbons. We use thermal desorption, photodissociation, and chemical activation methods to generate alkyl species. Then we studied the surface chemistry of these species. We studied methyl chloride, methyl iodide, and ethyl chloride on palladium-100 single crystal surfaces by electron spectroscopical method and thermal desorption spectroscopy. Several papers have been published on this field. We studied the methyl chloride in detail. The absorption of methyl chloride on palladium surface is very simple. It absorbs molecularly at low temperature and dissolves without dissociation. UPS showed that the molecular structure does not distort. From the work function data, we concluded that methyl chloride absorbs via its chlorine ends. Then we studied the activation of the methyl chloride by potassium. Potassium caused an increase in the strength of the methyl chloride to the surface. The methyl chloride dissociated, we identified the adsorbed methyl and chlorine species by this method. We got hydrogen, methane, C2 hydrocarbons, and potassium chloride distortion from the coadsorbed layer. We found stabilizing effects as well, but potassium stabilized the dissociation products. After this, we studied the effect of elimination of methyl chloride adsorbed on palladium surface at low temperature. We used high pressure mercury arc lamp for this measurement. methyl chloride dissociates about 15% in 1 hour. We got methane dissorption and found adsorbed chlorine on the surface that it was heated to the room temperature. We identified the adsorbed methyl by UPS, and we found the UPS peaks of adsorbed chlorine as well. The extent of dissociation was the largest in the monolayer and was the smallest when the contact layer was present. At this point, we reached the question of the mechanism of the excitation. 3 models are possible. Direct optical excitation of the adsorbed molecule, or excitation by electrons, which can be photoelectrons or hot electrons below the vacuum level as well. But because of the lack of the proper empty orbital of methyl chloride, the photoelectron process is more probable. In order to make sure, we made some measurements with the presence of reabsorbed potassium. We used several cutoff filters in this measurement. Cutoff filters removes photons, removes higher energy photons from the incident line. For tuning the work function of the coadsorbed layer, we use potassium reabsorption. We stated that the photolysis occurred when the maximum incident photon energy exceeded the work function of the coadsorbed layer and photoelectrons produced. Therefore, photoelectrons must play a dominant role in the photolysis of methyl chloride on this surface. The next topic is methyl iodide adsorbed on a palladium-100 surface. I show the thermal distortion spectrum of the molecular methyl iodide. We can see that under the monolayer coverage, there is no molecular methyl iodide distortion. It can be better seen on the insert of this figure. The uptake of methyl iodide was followed by Auger electron spectroscopy. We can see that the sticking coefficient is high and does not change up to the monolayer coverage. On the lower curve, we see that the remaining of the atomic iodine after heating up the sample to 300 K. The 2 curves run together in submonolayer coverages, and this means that methyl iodide dissociates completely in the heating process. We made some photoelectron spectroscopic measurements measurement at low and high metal iodide exposure. At submonolayer coverages and low exposures, we got the same peak as was observed on methyl chloride photolite on this palladium surface. So this peak we attributed to methyl group. At and over monolayer coverages, the peak structure of the molecular methyl iodide evolved. The iodine XPS peak show peak shift from the position of the atomic iodine to the position of methyl iodide. So we concluded that part of methyl iodide dissociates on palladium surface at low temperature, and this is followed by molecular absorption. On iodine XPS, we can see the thermal dissociation in the monolayer of methyl iodide. In the temperature range of 150 to 200 C, the iodine peak shifted from the methyl iodide position to the adsorbed iodide position. We can summarize the statement. This is the dissociation at low temperature and the dissociation of the molecular methyl iodide. In UPS spectra, we found no methyl peak over 260 P. So adsorbed methyl is rather unstable on palladium. It's dehydrogenated to methylene, methylene, and surface carbon. The main hydrocarbon form is methane, but we found traces of C2 hydrocarbons. The mechanism of the methane production is a point of question. Adsorbed methyl and the hydrogen produced in the structure of methyl can produce adsorbed methyl. But as I was informed, methylene can also participate in methane formation on some single crystal surfaces as well. We examined the absorption of methyl iodide over the desorption temperature of this molecule in methyl iodide atmosphere at high doses. We found intense peaks in iodine and carbon XPS region. The iodine peak belongs to the adsorbed molecular iodine, and here is the carbon peak. But we found no methyl peak in UPS measured parallelly. So this carbon peak must not belong to adsorbed metal because there was no sign of metal in nucleus. The peaks were stable when we evacuated the gas and disappeared when the sample was heated over so this carbon peak may belong to the adsorbed methylene or surface carbon. Methyl iodide can be photolized as well. These are the iodine spectra of the photolysis. Can be photolized easily. From the wavelength dependence of the photolysis, we established that photoelectrons also play an important role in this process. The last topic is ethyl chloride absorbed on the palladium surface. We can summarize the main effects. Ethyl chloride absorbs molecularly at low temperatures. When we heated the adsorbed ethyl chloride to higher temperature, about 1/3 of the monolayer dissociated. Dissociation takes place between 190 to 250, 270 heat. It caused large shift in XPS. And the ethyl chloride can easily be photolized. Let's see the evidences. This is the PBS integrated areas of ethyl chloride absorbed dissolved from the palladium surface. We see an absence of the distortion of molecular ethyl chloride. So this amount photolized, this amount dissociates. We can see the dissociation in the XPS region. This is the peak of molecular ethyl chloride, and this peak belongs to the adsorbed chloride, the product of thermal dissociation. A very pronounced shift was observed in the carbon region as well, at the temperature range of 190 to 260, 70 Kelvin. We made ocean measurement as well. The thermal and photodissociation of ethyl chloride was followed by the chloride Auger intensity. When a monolayer of ethyl chloride was absorbed at the temperature liquid nitrogen around it, and the sample was heated 300 K. Ethyl chloride dissociated. It is not the effect of the electron beam because every point represents distinct measurements. Then the adsorbed ethyl chloride monolayer was photolyzed, the extent of dissociation increased. We found some photodistortion, but it may caused by the change in the chlorine Auger fine structure as well. Since the chlor peak of the ethyl chloride has a peak shift in FPS, we can count the amount of the molecules photodissociated even at low temperature. At 90 K, the photolysis can be got easily, and we can see that as the photolyzed layer was heated to higher temperature, some additional thermal decomposition occurred. The products of photolysis cannot block all sites required for the thermal decomposition. We plotted the thermal desorption of ethyl chloride from irradiated multilayers. We can see that the products of photolysis destabilize the dissolved ethyl chloride and stabilize the multilayer. Thank you for your attention.
Oh, that was very clear. Thank you very much. Now, is there some discussion before we break for coffee? Yes, please.
I'm interested in the function of the chloride or the iodide in the decomposition of the alkali halides on the surface. It might be induced with the surface rearrangements or the change of oxidation state of palladium. Could you any comments on
The palladium surface was the same single crystal, but we can compare only the methyl chloride and methyl iodide, and methyl chloride does not dissociate on clean surface. So we can compare only the effect of illumination, and this was higher at methyl iodide, but we can't examine the effect of surface arrangement, because it was the same.
The basic point is how you differentiate the three positions associated with methyl groups or
photolyzed methyl chloride and heated to over the desorption temperature of methyl chloride, and we got a peak which we attribute to adsorbed methyl. And the same peak was observed when methyl iodide was laid on the palladium surface at low exposures, at low temperature as well.
Last question, Professor Hall.
Have you ever done an experiment where you've gone through the photolysis and forming the radicals and absorbing the hydrocarbons, and I take it the halide remains behind, and then repeated this over the same surface so that you have a higher poisoning effect of like chloride?
Interesting question, but we cannot do any experiment, but only examine the role of pre-adsorbed chloride on the absorption of methyl chloride, but not in photolysis. But some measurements were
What is the effect of
the adsorbed chloride arise the work function of the co-adsorbed layer, and the photolysis is
Okay, now thank you very much, Dr. Raybec.